Okay, so we're going to start looking at mathematics in Lean now. So I put in the chat links to the book and the repository. You can actually see the book through the repository itself. I'm going to assume you've all got code, you've all got it working on code spaces because I showed you how to do it this morning. Does anyone, if anyone needs more help on that, I'm sure people can circulate and discuss how to do it via code spaces.
Oh, this is.
Yeah. Because. Yeah. So I'm going to start sharing my screen.
Well, now I don't want to look at it though, because this is. This is a really serious problem, but do I not want to look at it because it'll be like the first thing I'm emotionally, and so I'll read it and be like embarrassed.
So I'm actually running mathematics in Lean.
So yeah, I just opened it again, but I closed it.
Oh, okay.
So okay. So I'm running mathematics on Lean actually locally, but it's the same thing if you're running it through code spaces as well. Since we're all here, I'm not going to go through the introduction. We'll just start with the basics, and then we'll maybe look at things like sets and functions. No, not basics. Yeah. So let's go to so I'm going to go to, so we're here in chapter 2 basics, and we're going to look at calculating Lean. So this is, I guess, in some sense similar to what Heather was talking about. So if we look at this problem, we've been asked to prove this, that A times B times C is equal to B times A times C, and we already have this issue about parentheses that was mentioned earlier. What's the difference between A times B times C and A times B times C with different parentheses? Well, one way to tell how things are bracketed, I think, did Patrick mention this, is that if you put your cursor in the info view window, it will sort of highlight things that are together. So yeah, so it's the multiplication is left associative. So we're just going to use commutativity of multiplication for real numbers, which is already given to us. So if we use commutativity of real multiplication of real numbers, that's this result here, and we can see what it says if we it's not real numbers, it's for commutative magmas, but but real numbers are commutative magmas. So so we apply that, and it just replaces the A times B with B times A. And then we're going to just apply associativity, and that completes the task. Now here, as you can see, we've actually specified what we're applying commutativity of multiplication to. We're giving it all of the inputs. And with Lean and most functional programming languages, you can sort of remove some of the inputs. That's still a theorem, but it's a theorem that's now quantified over a different variable B. But that, the rewrite actually understands what to do. Okay, so our next example is to figure out, using commutativity and associativity, what to do. Any suggestions here from the audience? What should we try? So what should I rewrite with first?
So you want to do it with rewrites?
Yeah, I think that's what we've been asked to do. I think that's how the game, how the book works, right? So are we going to do commutativity of multiplication or associativity? Any suggestions? Okay.
Commutativity.
Okay, let's try
C and B.
Okay. C and B. Yeah. Okay, yeah, so that's sort of the C and B round. So we can see, implication matters. Yeah. So that's changed those first two, and then what?
Associativity maybe.
Associativity?
Yeah.
And so in fact we don't again we didn't actually have to state what we've applied it to. And now what? Now what happens if I try commutativity of multiplication, is it gonna work or is it gonna happen? It didn't do what we wanted it to do because we want it to swap the C and the A. But it's actually done something else. It swapped the B with the C and the A. So what should we do?
Left arrow, or no, just focuses on C and A.
C and A? Yeah.
Yeah.
Or just the C and it figures out the A. Fabulous. Okay, so we've already seen this ability to, when we looked at the natural number game, to rewrite with hypotheses. So in this example, we're proving A times B times E is equal to C times D times F. And we can rewrite with a hypothesis that E equals F, replacing this E with an F. And we can apply, so we can't apply associativity of multiplication. If I tried that, it would say, give me an error message. Because it doesn't see the left-hand side of the associativity result. The associativity result has brackets A times B times C on the left, but we can apply it backwards using the left arrow, and you cut the left arrow \L like that. Okay, and then you can, yeah, I'm not going to go through all the steps from that proof. And I'm not going to go, yeah, since we don't have matters of time, I'm not going to go through all of the things here. You could check these yourself. I now want to look at calculation proofs. Okay, so I think Heather's been using calculation proofs a lot in her teaching. So we're going to prove this this result. So we're not seeing, if I put my cursor in here, we're not seeing anything in the info view window because this isn't a tactic proof. It's a proof term made through through calc mode. I guess if I just put in the word by, it would work. But then you can see what we've got to prove. So we've got to prove A plus B in brackets times A plus B is A times A plus 2 times A plus B plus B plus B, and we're going to basically rewrite the left-hand side as we do in ordinary mathematics until we get to the right side. We've got the left-hand side equals something or something. So this is the ordinary mathematics proof. We just have to fill in the sorries, and I guess in Heather's work she's got some clever tactics that, well, you just write whatever it is, but now we've actually got to do the results. So what I've skipped over is the results that we're going to be using. So we've got mul add, which is left distributivity, add mul, which is right distributivity, and we've also got the adder socks, and we've also got this 2 mul, which says that 2 times something is something plus itself. So any suggestions? Any of those things going to be useful? Mul add mul, or 2 mul, whatever.
Associativity over distributive.
Okay, so we'll use distributivity. So maybe it doesn't matter.
Repeatedly use this to open it.
Yeah, so we've got 2 options. Maybe it doesn't matter which we do. Let's just try one of them. Left or right? Is it distributivity?
Whatever.
Okay.
You're right, but
It will work for both.
that's not necessarily the justification for that line.
Okay.
Batsman said, then you will have to respect it.
Okay, so we haven't finished. So what's happened is it's rewritten the left-hand side, I guess. So it's opened up the times A plus B on the right, and it's changed it to A plus B times A plus A times B times B. We still have to make it look like this. So any further advances?
Again.
Let's just do it again.
The same one?
Yeah.
Yeah. Okay, so now that didn't work. So why not? So it's because,
Right.
yeah, that's right, because that's the other kind of distributivity. So we'll do add mul. So that's opened up the first term that was, in fact, we put the cursor just before, we can see what it used to be. And this is another nice feature of the info view window. It's showing you what's changed. So what's changed was this, with the parts in red. Okay, now what?
Do that one again.
Do that one again. Okay, so now it's squiggled out the sorry. It says that there is no goal to solve, so we can get rid of the sorry. Okay, so for the next line, we're going to prove that this equals this. And remember how the addition is left associative, so there are really brackets. It's a shame that when I put the cursor over it, sort of, yeah. But there are brackets around those first two sums. So what kind of thing do we have? It looks like a sum of it's a sum of a number of terms, 4 terms, and we've got a sum of 4 terms over here. This is the slightly annoying thing. And the question is it something, if you were writing a proof by hand, you would just say, oh, they're clearly equal, and you wouldn't do anything. But
Yeah.
That's ring, right?
well, yeah, I guess we could use ring. Are we allowed to use ring here? I'm not sure.
I think it's introduced later.
It's in, yeah, it's not.
We are adults.
It just uses the top.
Sorry,
Yeah.
has it been used? Has it been used before?
Oh, I doubt we can use ring because you can
Otherwise,
prove
yeah.
the whole,
Yeah.
prove every single theorem.
I mean, it is used later.
Yeah,
And that's the point.
yeah. So I think
Add a sock,
Yeah, that's.
repeat, rewrite, add a sock. That will do it.
Okay. Do
Probably.
we need the apostrophe there?
No.
Is that
Just
Okay.
repeat, rewrite,
They should be simplified as well.
okay? Yeah.
because repeat, rewrite, add a sock, just moves all the brackets to the very, very right on both sides.
Yeah.
And so it must work. If all the terms are in the right order,
So what's happened now? So we've got 2 goals.
it works. You
Yeah.
just need to delete the sorry. don't you?
Yeah. Oh, okay, I'm not sure what it's saying, 2 goals. Okay. Okay, so now what?
Where the AB equals to BA.
You need your 2 more.
Whatever the name is for the lemma that says A plus A is 2 times A.
Yeah, so that's 2 more.
But first they have to prove that A into B equals to B into A.
Okay, so we've got,
Oh,
And we'll add.
You're allowed to use congra there, but those goals are almost exactly the same. Right? So if you use congra, it'll just.
we haven't seen, okay, I guess we're introducing things we haven't seen, but yeah. So this is something that Heather mentioned, congruence. So,
Try congra too.
oh, yeah, that's not awesome. Yeah.
Try congra 3.
Okay, this.
that's the physicist approach to
Yeah.
It's cancelled the 3 things that were equal. Left you with the one thing that.
Okay, so that's not a tactic we were meant to have seen at this point. But okay, so now we'll just use commutative multiplication. Okay, so we've seen a few more tactics then. Anyway, but that's calculation proof. Oh, and I don't know if we've seen this. Yeah, so this is propositions are types. So we're seeing the type of the proposition power 2a. So the proposition power 2a is the statement that a squared is equal to a times a. So or just if you're a mathematician, it's just this is just what it's saying. So this is how you see what theorems are asserting. Okay, so here's the ring tactic. So this is what Kevin mentioned earlier. So instead of doing all of this faffing around with having to know the names of these results, you can just do ring, which will prove many things over commutative semi-rings. Okay,
But only if there are no hypotheses. That's the big problem. Like ring won't do.
Oh, yeah, so it can't use you can't use things in the context.
It won't do line 141.
Yeah.
Because you have to use.
Yeah. Yeah. Will Linda do that?
And polyrith will do it.
Which is, I guess we haven't.
It says, no, you're cheating.
Oh,
no, wait, is it
It
fast?
doesn't have the Python for calling Sage. I think polyrith like internally calls this Sage. Like I think it calls Sage running on the cloud and like gets the answer from there and like independently. It's complaining that the Python script is not installed on the system.
Oh, okay, so I don't have the right Python.
Does it then validate the results that Sage returns?
I believe so. Yeah, I believe it like post facto verifies.
Okay.
Yeah, that's some other point. Polyrith will be the linear, we could work out the linear combination, right? You do hype, take away hype primed, right? So you do linear combination, 1 times hype minus 1 times hype primed. That might solve it. If you want to solve it in one line. Because linear combination will do linear combinations of hypotheses.
Okay. So let's move on to the next tactic we were meant to learn, which is N3, right? So so let's just get rid of this here. So here we've got the hypothesis A plus B is equal to C, and we want to prove A plus B times A plus B is equal to A times C plus B times C. Now, what we could do is we could try rewriting with the hypothesis H, but what that will do is it will replace every instance of A plus B with C, and that's not what we wanted to do, right?
With the symmetric version of H,
Yeah, I guess that might work.
replacing all C's with A plus B.
Yeah. Yeah, I guess that.
And now ring will do
It
it.
has lengthy, it will a long way to go.
Okay, yeah, so that would work.
Yeah, it will work, but
Yeah, but we want to learn a new tactic, so we're going to learn instead this tactic,
The genie is out of the bottle.
which is N3, right? And that what that will do instead is it will instead of rewriting every occurrence, it will rewrite the second occurrence. And by second, we mean we're not starting at 0, we're starting at 1. It's very bizarre. So,
Bizarre.
so the first occurrence is A plus B. Okay, so now we're gonna.
Are there some naming conventions behind all the axiom lemmas with prime, prime, prime?
Oh, I don't know about the primes.
Where are the primes?
No, I mean, when you just did the auto completion,
Yeah.
you got, what was it, Malcolm prime as well?
What?
Or
What was it?
do I'm hallucinating?
Maybe, I don't know. So what?
Yeah, the admal, when you were typing the admal. Here, you have
LE mol prime
prime.
and LE mol.
Yeah, it's probably. Oh yeah, I don't know how. Yeah, so it probably depends upon what class. It's,
So do you, wait, go back.
what this one.
Go back to rewrite admal. I want to show you a trick that you may or may not know. Just like when you were in there, yeah, that context there. Yeah, now you did control space, maybe. You put your cursor after the L. Yeah, now do control space. And now move, and now don't click anything. Use arrow keys to go to add lemol prime. And now control space again.
That's for semi-rings.
And now you can hover over it. And we can see, there we go, yeah. So add lemma, that's A plus B is at most B times A. And then what's that? And if you now arrow keys go up,
Mhm.
and we can see, yeah, it's A plus B less than A times B. The right hand side, the variables are permuted.
Yeah. It's just the
That's the only difference.
Just one thing, can we show if it is real or integer print? Can we print the type real? Is it A or B, real or integer?
These are natural numbers.
Natural numbers, okay, and is there any way to print them along with
Here,
your
it's
output?
annotated.
Yeah,
But you can check as well, let's check.
Oh, yeah, well, I guess we could give this a name.
You can use the blackboard N and R in Isabel as well, but it's not that common.
Shameless plug.
No, just, that's the type annotation. Essentially, you could do something similar in Isabel as well, but you usually write real and not.
in our light, we have option to do it for every step. It shows.
So maybe I don't get what the question is. Okay, well, let's move on then. Okay, so
Typecasting basically.
we've seen some basic results about equations then over the real numbers. We haven't proved any of these, of course, we're just using them. So when we're looking at the natural number game, we began proving things, but a lot harder to prove for real numbers. So now we're going to, yeah, we've already seen the ring tactics. Oh yeah, so now a lot of the stuff we've seen holds not just over the real numbers, but over more general rings. I won't bother doing that. I think you can. Is there much to? Oh yeah, I suppose that yeah, this halve tactic is useful to know. Okay. So let's see how this works. So we're going to prove that A times 0 is equal to A. And in doing that, we're going to introduce an auxiliary result and prove it, right? So what we're going to do is we're going to, first of all, re-express A times 0. So this is a result we're going to prove. But A times 0 plus A times 0 is A times 0 plus 0. And we're going to then use that result in proving the original result. So to prove this, we'll just start with distributivity. So we'll use distributivity to replace that. So we've got A times 0 plus 0. And of course, we can replace the 0 plus 0 with 0. And then we'll replace the something plus 0 with itself. Right. So that's introduced now. So we can see here our context, which has all of these hypotheses. We've got this new hypothesis that we've proved, and we're going to use now this result called add left cancel. So add left cancel, which I guess we proved earlier, which says that if you've got
We confidently, sorry.
yeah. Sorry?
We confidently proved it with a sorry.
Oh yeah, okay, we didn't prove it. We didn't prove it, but we should have proved it, yes. So we've got essentially something, yeah, so let's look back, yes, let's see, we'll do what Kevin suggested. Oh, wait. It's already there, isn't it? Yeah. So this is what add left cancel says, which is that if A plus B is equal to A plus C, then B is equal to C. So we're going to use that result
Cancel.
with H to cancel out the A plus A times 0 on the left. And that gives us the result we wanted. Okay. So, shall we do something similar then to prove this? I mean, I guess we could just do commutative multiplication. Well, that's probably the simplest thing to do. Well, okay, I guess we'll just do that. Ah, it looks like we don't have it. Excellent.
No, we don't.
Okay, good. In that case, we can't do that. So shall we do something like the proof above? So any suggestions? So we will maybe some auxiliary result, yeah. 0 times A 0 times A.
Reverse engineering.
0 times A plus 0.
And why don't let's suppose we have proved that. So what we'll do is, yeah, this is like one way to prove things, assume you've already proved it. And then if we had proved that, what would we then do?
Hope to copy paste the previous one.
Copy and paste. Okay, and that seems to work. So now we've got to fill in this proof. So
Or I copy paste and fix it.
by copying and pasting and fixing it. Okay. Oh. Okay, so everything works up till add 0 up here. Oh, that's not
Oh, wow.
going like that.
Maybe we want to fix it. We used the wrong distributivity.
Well, yeah, also, is it true? Yeah. So we can use something.
1, 0 can be used. First, use convert 0 into A to 0 and then use 1, 0.
Sorry, what was the suggestion?
I mean,
Because null 0 is only 0.
you can convert 0A goal into A0 and it will be like null 0.
We don't know that commutativity.
Multiplicative 0 into A equals to we cannot.
Well, so perhaps we should try having a different auxiliary result, because I suppose why this worked because we were doing add left cancel and now we've changed the direction of things. So is there maybe a different auxiliary result you might want to try?
0 plus 0 times A to have a right function.
Yeah, so what, so we're going to have 0 plus 0. Okay, yeah. And we'll sorry that out. Okay, so that seems to work. So now let's try to fix up this argument. Is that doing anything useful? Any other suggestions?
Use the other distributivity.
Add one. Okay.
Whichever one we
So that's not working.
backwards.
What add maybe?
Okay, brilliant. So now what do we do?
Add 0.
And presumably we've already
Zero
proved
out.
0 out. Okay, and that's that. Fantastic. Right, so we've seen how to prove auxiliary results. I'm going to skip over all of this. I guess this is some stuff on groups. So now this is roughly, okay, it's not exactly how groups are defined well, you can see the definition. It's not very helpful, it's not going to be very informative, but let's just see the definition of group. So if we look at the definition of a group, so a group is a class of objects, and it says here that it extends div in monoid G. So let's see what that is. Okay, so this is div in monoid G, so which extends monoid G in G div G. So we've got well, these things are actually proofs of results that we've got. And if we look at monoid G, I think it's probably going to be most useful. All right, so we've got,
Wait, they're not proofs, they are
What-
requirements.
yeah, requirements. Well,
Assumptions, axioms, however, but I mean, they're not
Well-
properties. I mean, you're saying the operation has.
yeah, well, yeah, because here's the
There's the proof.
here's the proof. Because yeah, it's extended another class and then it's introduced some facts concerning this class. So let's go to semi-group. That probably actually. Okay, so here's the thing that doesn't have. So this is the actual property. Yeah. So semi-group. A semi-group is something that has this property, associativity of multiplication. Right. And all of the other properties, I guess, come from. So that probably the other property came from. How do we go back? How does one go back? Is there a back? Maybe some. Yeah. Okay. Then we've got mol1 class. Okay. So the 1 mol class gives us this, the 1 mol. Yeah. And
Oh, okay, protected can be proven or it can be just, okay, I see it.
yeah. Okay.
Have a little bit, there's a proof attached.
Yeah. So yeah. So we've begun to see how one defines mathematical objects in Lean. And usually you build it up from very basic objects. But anyway, so let's just using these three properties of group. Let's try proving this. What is going on here? I guess I'm in the wrong. Wait. Okay. Yeah, so we're going to prove this. A times A inverse equals 1. And that's not one of the properties that we're given. So we have Massot 1 mol and mol left in.
Isn't this hard?
Yes, yeah.
I mean, that's the way how you do it with your first year students.
That's the way that John Thompson did it with me. But that's not the way that we teach as Imperial. We tell them there's 5 axioms for a group. And we don't put them through this hell. Is this really the first theorem you want your undergraduates to see in group theory? Isn't the proof like 5 lines long?
Yeah, well, this is mathematics in Lean, so.
Multiply by 1 at the start.
It's more or less how my analysis lecture was in the first year.
We need to multiply by 1 at the start. And then have an
Okay,
A
so
inverse, A double inverse, A inverse.
shall we do a proof by calculation then? Let's.
Yeah, okay.
So we'll do it A times A. Oh, to do the inverse, it's backslash either I and V or backslash -1. And we'll do an equals, and I'll just write sorry, and then equals sorry. And then the last line is going to be an underscore equals 1, and then equals sorry. So that's how we'll template the proof. We'll get rid of that last sorry. Okay, so we've got that. So we're going to do a 1 at the beginning.
Yeah.
Okay.
What's the proof? Who's leading this proof? What can you tell me? How does this proof go in maths? Forget about the Lean.
You're going to replace that 1 at the start now with A double inverse, A inverse,
Aha.
and then cancel the middle term and then cancel the end.
But now you've got to prove then use associativity.
Yeah.
Yeah, this looks great. Yeah, very nice.
Yeah, so what we'll do is, as Kevin suggests, we won't do the leads. We'll just do the sorries for the moment. And then what's the next step?
We're going to need to move some brackets so we can cancel the middle terms.
Yeah. So now we can't do all the let's see.
I'm adding an extra line if we need it.
Fine, just do the whole thing. The proof is gonna be by repeat, rewrite, Massot.
Yeah, we could, yeah.
Rewrite
okay,
Massot
yeah,
just takes all the brackets on both sides, moves them all to the right.
Yeah, okay.
They will be equal. Just keep the terms in the right order. Repeat, rewrite, Massot is your.
Gihan is just happy that none of his students is in the room.
This is a man who doesn't have time to fast.
Okay.
That's one.
And then I guess that's gonna be A inverse.
Yeah.
And A inverse. Okay, so let's try filling in all the bits and pieces. So the first thing is rewrite one mol. Is that right? No, that didn't work.
You're it.
Oh, by. Okay, let's start with by. Okay, so what's the next one?
More left inverse. We've got two rewrites now. There's a double read.
So,
There's one
oh,
probably
two, re-
too
two,
much.
two rewrites, yeah. Two rewrites, yeah. No, so we said we're gonna do repeat.
Rewrite Massot.
Yeah.
Simp.
Okay, yeah.
One. Wait. Cheat.
Oh,
Yeah.
so we don't have one mol, yeah. Oh, and we don't have one mol one, okay. So we need to do associativity.
So you can put the, on line 139, you can put the brackets. You put the brackets in the right place on line 139.
This is the one, right?
Yeah, because repeat, rewrite, Massot is always going to work. Then you can put them, yeah.
My brain.
Okay.
So many parentheses.
Okay.
There you go. Is that really the first thing you want your students to see in group thing?
I don't know if this is, I don't know if this is meant for undergraduate, so is mathematics and English undergraduate? Is this
In the audience, the people who.
No, this,
Who at least-
I think if this, no, this is what Patrick and Jeremy Avigad wrote.
Yeah.
This isn't my thing.
But in some sense, the
In when we did it in the sessions, we did this one.
I would
No,
have.
I think I gave you,
We had a few more things.
oh, maybe.
no, you're right. It's part of Gihan's modern maths game. You have to do this.
Okay, I did.
He does lead you through it a little bit.
Yeah, maybe I did give this to my undergraduates.
But I'm not sure.
Yeah, if you walk through it, it's a different story though.
Yeah.
The second thing we did was that if you have Massot and one mul and mul right in,
Hmm.
then you have to prove that it doesn't give you a group.
Okay. So, let's see, yeah.
But I would say that looks pretty much to what we did in my first year, let's say in week 8 or so of term 1.
Okay.
Before the Christmas break.
So we're gonna learn a new tactic, which is called apply. Well, I don't know, is that what we're meant to learn? Yeah, I think it is. We're meant to learn apply here. So we have these results concerning inequalities. So this one just says that less than or equal to is reflexive. This one says it's transitive. We've got a few other things. Okay. So we want to prove that A is less than E, and we could do it forwards. I think Heather is suggesting that we should only do forwards proofs because that's how people do things, but it's easier to do backwards proofs in a theorem prover, so we'll,
Talk to that guy over there.
okay. So, so let's see, so what we could do is just say we can prove this by some kind of transitivity style result. So we know that something is less than E, like this D is less than E. I mean, can we check, well, first of all, let's do it forwards. So can we chain these things together to prove that A is less than E, and which of those things are we gonna chain together to prove that A is less than E?
Do you want some halves?
Yeah. Oh, well, I think we're gonna do it backwards. We're gonna do it backwards.
wanna do it
Yeah, I think that's what we're supposed to be doing here.
Okay.
Yeah.
Well, then I guess you want to apply your less than transitivity.
Yeah, so, and which one are we, yeah, so we're gonna apply less than transitivity.
And then give us some new goals.
Yeah. So let's see what the applied tactic does, right? So the applied tactic does this. We want to use this theorem less than trans. And what it does is it looks for the conclusion of the theorem, which is less than trans, and the conclusion matches the goal. I guess it's called unification or something, I don't know. So I'm not a computer scientist. Okay, so it somehow matches the computer science, tell me what I'm doing. It matches this thing. So then what it does is it introduces new goals to match the I guess the requirements, the hypotheses of this, the arguments of that theorem. So we can see two new goals. We need to prove A is less than question mark B, because it doesn't know that the B isn't the B, it's just some new variable. A is less than something, and we want to prove something is less than E. And so the way you can work, if you want to separate out goals in Lean 4, you can use this \dot. So we're going to work on the first goal now. We want to prove A is less than something. So can we prove A is less than something? We're going to prove A is less than C. So what result are we going to use to prove A is less than C? We'll apply some result. Well,
LT of LE of LT.
yeah, so we don't want to use the LT trans because we don't actually have the hypotheses to use that. So we'll use apply LT of LE of LT. What have I done wrong then? Oh, I've just got an extra goal result, yeah. No? I've done something else wrong. What else have I done wrong?
It's worrying about.
Oh, I did, yeah, the meta variable, yeah. So there's a.
So what are you applying
yeah.
it to? And we could directly apply to H0 and H1.
Or I'm just going to put in an extra, sorry to shut out for the moment.
You do fat line.
A fat line, oh, what?
Put an F before the apply and it will put the goals in a more sensible order.
Oh, okay.
Yeah.
And then, oh, it's still giving me the.
Oh wow, now you get some crazy thing.
Okay, I'll
That idea, yeah.
I'll just do the apply.
Given that we know where that's coming from, do we want to just apply it directly to H0 and H1?
I mean, once we put in the first goal, then it will resolve the meta variable that it can't figure out. So we're going to.
Is have to do
Yeah.
with this.
So we want as goal as the form A is less than or equal to something, and we've got one which is H0. So we'll do exact H0, so the exact tactic. Okay, so now we don't have any error messages, so it's figured out what the meta variable should be. Okay, so now we want to prove B is less than something, and which result do we use? H1, so it's exact H1. And now we've got to prove C is less than E. So what should we do now?
Looks like the same thing
Yeah,
with H2 and H3.
So we'll apply. I mean, so what we could do is we could do it all in one go. So let's just do exact And I'm gonna use this neat feature of pinning, so I'm gonna pin that so that as I type, it doesn't get rid of what I'm typing. So we're gonna apply what it will do exact and what result we're using.
Turn off less easy.
And it's H. Okay, I'll unpin that. Yeah. And in case it wasn't clear how the naming convention works, like why is it called LT of LE of LT? So here we're trying to prove a less than result, and the of is just used to refer to the hypotheses. So it's a less than of a less than or equal to, that's the LE, and then of the LT. So that's just how the naming convention works. And once you learn the naming convention, it's fairly easy to find results. It's quite a clever convention.
So I wonder, for those who want to, maybe it's an opportunity now to just have a little more explore of maths in Lean.
Yeah.
But the point is that the game engine is great for introducing some of the basic tactics and introducing students to it. But if you're going to do serious maths, you want to be playing with this sort of editor and the goal state, etc. And the Maths in Lean book takes you through some rather complicated mathematics. So
yeah,
it is an excellent resource.
Yeah, it's maybe more fun. Some of the earlier chapters are not so exciting, but then it gets more interesting when we get to the later part. Okay, so yeah, we will just let people play.
So I guess, yeah, for those who want to play and have a bit of support with it, we'll be around. For those who want to call it a day, that's also okay. There's lots and lots of food still, so do take bundles of crisps with you as you go, etc.